What if the only reason quantum mechanics exists at all, like the only reason we have this super fuzzy, probabilistic, microscopic reality is just because our universe is expanding into a hidden fifth dimension?
Yeah, that is exactly the kind of question that usually gets you politely escorted right out of a university physics department.
Right, yeah. Like, please pack up your desk.
Exactly. Because, we're trained to think of general relativity and quantum mechanics as these two fundamentally incompatible operating systems.
Mm.
I mean, one is this framework of smooth, continuous geometric curves describing gravity and space-time, right?
Yeah, the macro world.
Right. And the other is, well, it's a discrete, jittery casino where particles exist in superpositions. They just don't mix.
And for, gosh, a century now, the holy grail of physics has been trying to write a patch that makes those two operating systems talk to each other.
The quest for quantum gravity.
Exactly, quantum gravity. And usually the attempts to unify them involve incredibly dense, entirely new mathematical architectures like string theory or, loop quantum gravity.
Yeah, you basically have to learn a completely new mathematical language just to read the map.
Right. But the source material we are doing a deep dive on today takes a radically different approach. It doesn't throw out the old map at all.
No, it really doesn't.
It asks this wild question. What if the unification we are desperately looking for is already hiding inside the classical geometry of general relativity and we just, haven't looked at it from the right dimensional angle?
It's a fascinating premise.
It really is. So, since you, our listener, are already well versed in university level mathematics and theoretical physics, we are going to dive straight into the deep end of the tensors and operators today.
No water wings today.
None at all. We are exploring a recently drafted paper by an anonymous author. It's simply titled Lorentzian Cosmological Model.
And just for context, this draft accompanies a much longer work, but it stands completely alone to explore a very specific, honestly very strange metric constraint.
Yeah, the central mission of this paper is to trace this really fascinating mathematical journey. Like, we begin with a generalized four-dimensional Lorentz transformation,
Right.
and then we basically watch it morph into a five-dimensional scalar flat cosmology.
Which is an elegant mathematical move in itself, but
Uh,
then,
yeah, the part that genuinely made me put the paper down and just stare at the wall for a minute. We see it culminate in a time-dependent Schrödinger-like equation.
it is wild.
It is. We're going to unpack how macrocosmological evolution inherently dictates microquantum behavior all through the geometry of an extra dimension.
So to build this new cosmology, we have to start by, well, tearing down the foundational grid of space-time and rebuilding it.
Right, we are moving away from the familiar Minkowski space into something highly customized.
Exactly. The author sets up the initial problem in a standard four-dimensional grid, which we can just call the grid X.
So the grid X equals the tuple X naught, X1, X2, X3, where X naught is obviously time and the rest are spatial coordinates.
Yeah, standard setup, nothing controversial there. But then they apply a transformation, which they label lambda.
Okay, and this transformation applies standard Lorentz constants, right? The velocity parameter v and the Lorentz factor gamma.
Right, and we know these satisfy the classic Lorentzian identity, where
Hmm.
gamma squared times the quantity 1 minus v squared equals 1.
Yeah, that identity is basically the bedrock of special relativity. I mean, it's what ensures the speed of light is constant for all observers.
It is, but the author uses this to generate a completely new diagonal metric tensor. And this is where the geometry immediately starts to show its teeth, so to speak.
I'll say. The metric tensor they derive, which they call gimu nu, is a diagonal matrix. And the spatial components are all simply scaled by the parameter v, so v down the diagonal.
Right.
But the time component is scaled by -1 over v.
Yeah, let's just pause and visualize the physical implication of that metric signature for a second. In standard flat space, your signature is essentially a static -1, 1, 1, 1. But here, v is acting as like a master parameter that intrinsically links the scaling of time and space.
It's an inverse relationship.
Exactly, because the spatial dimensions are scaled by v, and time is scaled by the inverse of v -1 over v. It means that as the parameter v changes, space and time cannot evolve independently.
Oh, right. So if v is increasing, your spatial dimensions are actively expanding, but your temporal dimension is compressing.
Yes. Time is dilating in direct opposition to the expansion of space. They are completely locked in this geometric seesaw.
I mean, I followed the math up to that point. It's a really elegant way to model a coupled expansion. But then Then I hit definition 1.3, and I have to be honest, I initially thought it was a typo in the math.
The metric loosening transformation.
Yes. The author introduces this metric loosening transformation, denoted as gamma sub b, and without much fanfare at all, we are suddenly thrust into a five-dimensional grid.
Yeah, the author calls this new grid U prime, and it consists of time, t, a brand new extra dimension they labeled W, and then our standard x, y, and z.
And look, I am generally fine with adding extra dimensions to solve cosmological problems. I mean, Kaluza and Klein did it a century ago to unify gravity and electromagnetism.
Right, it's a standard tool.
It is. But here's what I really need to challenge you on. The author doesn't just add this dimension orthogonally. They explicitly insert a frame-dragging term, a time-dependent function they call beat of t, into the cross terms of the metric.
Yeah, they do.
They set the time w and the w time components of the metric tensor equal to this function b of t. So gtw and gwt both equal b of t. What is the physical justification for that? I mean, why are we forcibly dragging time into a brand new extra dimension?
It definitely looks like a hack at first glance, I agree.
Great.
But to understand the physical justification, you have to look at the massive cosmological headache that it cures. When you tack on an extra dimension orthogonally, like just perpendicularly without any coupling, you're essentially just giving space-time a flat, empty parking lot.
Yeah.
It doesn't interact with the four dimensions we live in. It doesn't solve any of our curvature problems.
Like the Big Bang singularity, for example.
Precisely. In standard models, dealing with the Big Bang is a total nightmare because as you wind the clock back, the curvature of space-time approaches infinity. The math literally just breaks.
Everything goes to infinity.
Right.
Yeah.
But by introducing that frame-dragging term, B of t, the author is non-trivially linking the evolution of time directly to rotation or movement in this fifth dimension, W.
Okay, so as time marches forward, the universe is inherently twisting into this W dimension.
Yes. Think of space-time as a highly tensioned fabric. In standard four-dimensional cosmology, an expanding universe stretches that fabric, creating massive curvature stress right at the origin point. But by coupling time to this fifth dimension, the author provides a release valve for that curvature. The brilliant mathematical payoff of setting those cross terms to B of t is that it forces the entire overarching five-dimensional metric to be scalar flat.
Okay, let's break down scalar flat for a second for the listener. That one's the Ricci scalar, which is the single number that describes the total curvature of a space at any given point, is exactly zero everywhere.
And that is a theoretician's dream.
Yeah.
You have constructed a universe that is permitted to expand because our parameter v is still driving the spatial scaling, but it remains globally flat because the structural twisting into the fifth dimension absorbs and perfectly balances out the curvature of the expanding four dimensions.
So you have engineered a mathematically smooth, entirely singularity-free environment.
Exactly. The space is essentially self-correcting.
And you can really see the sheer power of this move when the author calculates the Einstein tensor for this new five-dimensional space. I mean, the Einstein tensor is notoriously brutal to calculate by hand once you start adding dimensions and frame-dragging cross terms.
Oh, it's usually pages of algebra.
Yeah.
You expect a massive, chaotic matrix of partial derivatives.
But here, almost everything cleanly cancels out.
It is a profound simplification.
It really is. When the dust settles, all the spatial curvature components of the Einstein tensor vanish completely. They just go to zero.
Right.
The only components that survive are the purely temporal components. So the TT component of the Einstein tensor, or GTT, and the mixed time W components. And they are entirely determined by the interplay between V, our expansion parameter, and B, our frame dragging parameter.
Yeah, and I want to focus on why that cancellation is so deeply important.
Go for it.
In general relativity, the Einstein tensor tells you how space curves in response to energy and momentum. By forcing all the purely spatial components to vanish, the metric is telling us that the underlying geometry of the universe's expansion doesn't generate localized spatial warps.
Okay.
The cosmological dynamics, the actual engine of the universe, is entirely isolated within the relationship between time and that hidden fifth dimension.
Oh, wow. It's as if the complexity of the universe's expansion has just been swept under the five-dimensional rug.
Pretty much.
But it works, which of course leads us to the next obvious question. If you have this beautiful self-correcting scalar flat metric, you want to know what it looks like in a pure vacuum.
Naturally.
You want to test the boundary conditions where the Einstein tensor doesn't just simplify, but completely zeroes out.
Right. A null Einstein tensor means We are looking at the pure, unadulterated geometry of the spacetime without imposing any external matter or energy fields. We are asking the math, what does this universe want to do all by itself?
And the math gives a very strict answer. In section 1.2, the author shows that for the Einstein tensor to be identically null, our frame-dragging term, b of t, has to obey a very rigid constraint.
Yes, it does.
It must equal a constant k times the square root of v, all divided by the first derivative of v with respect to time.
And that is a phenomenal constraint, mostly because of what it forbids.
Well, the first derivative of v with respect to time is sitting right there in the denominator.
Exactly. This is the math dictating reality.
Mm.
If the universe were static-like, if it wasn't expanding or contracting at all, then the parameter v would be a constant, and the derivative of a constant is 0.
Right, and if that derivative in the denominator goes to 0, the frame-dragging term b of t blows up to infinity and the entire metric collapses.
Right. Therefore, the universe is absolutely forbidden from being static. It must be dynamic. Furthermore, because of the nature of the square roots involved in the derivation, v is forced to be strictly positive, and it must continually grow within a bounded range between 0 and 1.
The geometry essentially acts as a cosmic engine that refuses to stall. It has to keep moving.
Exactly.
And to demonstrate what that looks like, the author proposes a toy model for this cosmic evolution. Here's where it gets really interesting. They define this evolving scale parameter v with a simple exponential function.
Yeah, in section 1.4.
Right, cosmology under lambda naught. They propose that v of t equals 1 minus e to the power of negative lambda t, where lambda is strictly greater than 0.
What's fascinating here is that it is a classic asymptotic curve, and it maps onto our intuitions about cosmic evolution beautifully.
Let's trace the life cycle of this toy universe. At the very beginning, when time hanging equals 0, that exponential term becomes e to the power of 0, which is 1.
Right.
So v of 0 is 1 minus 1, which is 0. The universe starts at a scale parameter of exactly 0.
But notice the difference between this and standard Big Bang cosmology. In the standard model, a scale factor of 0 implies infinite density and broken physics, a true singularity. But here, because we are operating within a 5-dimensional metric that is globally scalar flat by design, the mathematical machinery survive that initial 0 state. It is a singular origin, sure, but it is a geometrically safe origin.
And then as time marches forward, that negative exponential term gets smaller and smaller. So v of t begins to rise fast at first, and then it slowly tapers off.
Right.
As time approaches infinity, the exponential term approaches 0, meaning v asymptotically approaches 1.
Think about the elegance of this. By demanding the Einstein tensor be null, the math dictates a universe that must be dynamically evolving, not static. Look at the physical narrative that toy model is painting.
Okay.
At the birth of the universe, the derivative of v, which is the rate of expansion, is at its absolute maximum. It's an explosive beginning. But as the universe ages, that expansion gently coasts, slowing down over billions of years until v flattens out near 1.
And the frame dragging into the 5th dimension acts as the great cosmic regulator.
Exactly. It allows this massive deceleration to happen without ripping the space-time fabric apart.
It is a universe that wakes up violently, expands rapidly, and then slowly goes to sleep as its geometry flattens. It's a beautifully compelling model.
It really is.
But, there is a hidden cost to this setup. If the universe's foundational geometry is constantly evolving like this, constantly sliding along that asymptotic curve, how can we possibly define stable physical rules inside it?
You are hitting on the fundamental problem of symmetries. In physics, you cannot separate geometry from conservation laws. They are intrinsically linked.
Let's unpack that, because it's crucial for where this paper goes next. In physics, we rely heavily on killing vectors. For the listener, a killing vector field essentially maps out the directions you can move through a spacetime without the underlying metric changing.
Right. It's a mathematical description of continuous symmetry.
Exactly. And through Noether's theorem, we know that every continuous symmetry in nature corresponds directly to a conserved quantity. Like, if your spacetime has spatial translation symmetry, meaning the rules of physics don't change if I move 10 feet to the left, then momentum is conserved. If it has rotational symmetry, angular momentum is conserved.
And most importantly for this paper, if your spacetime has time translation symmetry, meaning the metric doesn't change as you move forward in time, you get the conservation of energy.
Right. To have a universally conserved concept of energy, you need a valid time-like killing vector.
But we just established that our universe is fundamentally dynamic. The parameter v is constantly growing. So defining a time-like killing vector in this evolving frame-dragged five-dimensional space is going to be incredibly difficult.
And the author explores this by looking at an alternative constraint for our frame-dragging term in section 1.3. They constrain b to equal the first derivative of v with respect to time divided by v.
Right, b equals dot v over v.
Exactly. And this allows them to define a time-like killing ansatz, a specific vector field, EA, within the five-dimensional grid. But the mathematics imposes a brutal spatial restriction. The region where this vector field actually remains time-like is not infinite. It is bounded.
Yeah, the math gets very weird here, very specific.
It does. The author proves that the vector field is only time-like if a certain spatial constraint is met. The radius squared, which is x squared plus y squared plus z squared, must be strictly less than 4 times eta over the quantity epsilon times v.
Let the implications of that sink in for a moment. The radius of the valid region is inversely proportional to v.
Right, because v is in the denominator. So imagine standing under an enormous open umbrella. That umbrella represents the pocket of the universe where energy conservation holds true.
Okay, great analogy.
But because the parameter v is in the denominator of our spatial constraint, and we know v is continuously growing as the universe ages.
The umbrella is slowly closing.
Yes. The radius of the stable time-like region is physically shrinking over cosmic time. So what does this all mean? Why would an evolving universe have a shrinking region of time-like symmetry?
Well, it is a deeply destabilizing concept from a thermodynamic perspective. We are taught that the first law of thermodynamics energy is neither created nor destroyed, is absolute.
Right, it's like physics 101.
But this metric suggests that in an evolving universe, the domain where that law applies is actively collapsing. It forces us to confront the fact that our macroscopic assumptions might just be localized illusions.
Wow.
Think about the early universe in this model. When v was incredibly small, just after k equaled 0, that denominator was tiny, meaning the radius of valid time-like symmetry was virtually infinite.
Oh, I see. So in the deep past, energy conservation was a global, universal truth.
Exactly. But as the universe expands, and the frame dragging against the fifth dimension intensifies to balance the curvature we talked about, the pocket where time translation symmetry holds true gets tighter and tighter.
So as v asymptotes toward 1, the boundary of that valid region shrinks from infinity down to a finite, measurable shell.
Yes. And outside of that shrinking boundary, the killing vector is no longer time-like. It becomes space-like.
Meaning an observer out there wouldn't even agree with us on what the word energy means because the foundational symmetry required to define it is literally broken for them.
Right. It paints a picture of a universe that is fundamentally isolating over cosmic timescales. It is slowly forgetting its own rules.
That is wild. And this is the profound cost of the metric loosening transformation we discussed earlier.
Yeah.
You buy a singularity-free scalar flat expansion by embedding the universe in 5 dimensions, but the price you pay is the gradual localization of your thermodynamics. Your foundational symmetries become shrinking islands in an expanding sea.
Beautifully put. And a terrifying thought.
Right, but wait, if the macroscopic universe is this chaotic, evolving place where even energy conservation is becoming localized, what happens to the microscopic world? Because this entire paper has been a setup for the ultimate magic trick.
It really has.
We've established the macrocosmology. Now, what happens if we drop a single, simple quantum field into this geometry?
This is the pivot. This is where the paper stops being just an intriguing cosmological sandbox and becomes a potential bridge to quantum gravity.
Yeah, so we get to definition 1.5, where the author introduces the box operator. For those listening, the box operator, or the D'Alembertian operator, is essentially the wave operator generalized for curved spacetime.
Right.
The author applies this D'Alembertian operator to a simple scalar field, which they call phi.
Now, in standard flat space, applying the wave operator to a scalar field is straightforward. You get your standard spatial derivatives, the Laplacian operator acting on phi, and your standard time derivative.
Yeah.
But in this metric, it is a mathematical nightmare.
Because of the frame dragging, right.
Exactly. The function b of t, which links time to the fifth dimension of w, guarantees that the time derivatives and the w derivatives are heavily cross-contaminated.
They're all mixed together.
Yeah. The D'Alembertian operator spits out a massive, tangled differential equation with mixed derivatives of time and the extra dimension w. Solving for the wave behavior of the scalar field phi directly in that environment would be algebraically atrocious.
But theoreticians have tricks for this. The author uses a classic conformal rescaling to clean up the mess. They basically redefine the field itself.
Right.
They declare a new field, psi, which is defined as the original field phi multiplied by the expansion parameter v raised to the 3/4 power.
It is a highly specific mathematical sleight of hand. By absorbing the expansion parameter directly into the definition of the wave field, the chaotic, cross-contaminated terms in the D'Alembertian opulator are cleanly factored out.
The equation simplifies beautifully.
It does.
It's a great setup, but it's what they do next that constitutes the actual paradigm shift in this paper.
Yeah.
The author looks at that extra dimension, WU, and they invoke the Kaluza-Klein mechanism. They compactify it.
Yes, this is the crucial step.
They take that fifth dimension and roll it up into a tiny microscopic circle, which they denote as S1, with a constant radius of r.
And compactification has immediate, profound consequences for any wave existing in that space.
Yeah.
If you have a wave traveling around a closed-loop circle, it can't just have any random wavelength.
Right.
It has to meet itself perfectly as it completes the circuit.
Yeah.
It has to resonate.
Like plucking a guitar string. The string is clamped at both ends, so it can only vibrate at specific harmonic frequencies.
Precisely the same logic. Because the dimension is a circle, the momentum of the field psi along that fifth dimension becomes quantized. It can only take on discrete values.
Okay.
The author mathematically represents this by introducing an integer winding number n, where n is not equal to 0.
Right.
The field can wrap around the fifth dimension once, twice, 3 times, but it cannot wrap around 1.5 times. The momentum is locked into discrete integers.
So we have our cleaned up, conformally rescaled wave operator acting on CI, and we plug in this discrete, compactified fifth dimension. And when the author evaluates theorem 1.4, the result is absolutely staggering.
Yeah, it really is.
I remember staring at the final equation, blinking, because out of this purely classical, higher dimensional geometry, the author derives an effective Schrödinger-like equation with time-dependent coefficients.
And not just a generic wave equation that looks a bit like Schrödinger. It is the fundamental equation of non-relativistic quantum mechanics, complete with an effective Planck's constant, an effective mass term, and a potential energy term.
Unbelievable.
But because it was derived from our evolving cosmological metric, those coefficients are entirely time-dependent.
Let's meticulously detail these effective quantum parameters, because this is where the unification actually happens. In our observable reality, Planck's constant is the bedrock of quantum mechanics. It is the number that sets the scale for quantum uncertainty, the fuzziness of the microscopic world.
Right.
But in this geometrically derived version, the effective Planck's constant H effective is dictated entirely by the expansion rate of the universe. Specifically, the math defines H effective as the first derivative of V with respect to time.
If we connect this to the bigger picture, connect that back to the toy model of the universe we discussed earlier.
Right. In the toy model, the derivative of V, the rate of expansion, starts at its absolute maximum at the very birth of the universe.
Which means, according to this derived Schrödinger equation, the effective Planck's constant at the Big Bang was massive.
Oh, wow.
The fuzziness, the quantum uncertainty, wasn't just a microscopic phenomenon. It was a dominant macroscopic feature of the early cosmos. Reality itself was deeply, violently probabilistic.
But then as the universe ages, the parameter V follows its asymptotic curve. The expansion rate slows down, the derivative of V drops closer and closer to 0.
And as it does, the effective Planck's constant shrinks alongside it.
That is mind-bending. It implies that quantum mechanics isn't some eternal, separate rulebook that sits outside of gravity. It implies that the universe is actively becoming more classical as it ages.
Yes.
The macroscopic expansion of space is physically dampening the quantum fuzziness. And if we follow the asymptote to its logical conclusion, when time reaches infinity and the expansion completely stops, when the derivative of V hits exactly 0, the effective Planck's constant becomes 0.
And a Schrödinger equation with a Planck's constant of 0 collapses entirely into classical mechanics. The quantum realm simply turns itself off. Wow. It is a stunning physical interpretation. Quantum probability is just a transient geometric consequence of the universe dragging itself through a higher dimension.
I am still trying to wrap my head around a fading Planck's constant, but the derivation of the mass term is arguably even more profound.
I agree.
In the standard model of particle physics, mass is a messy concept. Particles get mass by interacting with the Higgs field, and the values seem almost arbitrary. But in this derived Schrödinger equation, the effective mass of a particle is entirely geometric.
Walk us through the proportionality on that.
The math dictates that the effective mass, m effective, equals v squared times n over r. The square of our expanding scale parameter v multiplied by the winding number n divided by the compactified radius of the fifth dimension r.
This is the realization of the deepest hopes of Kaluza, Klein, and modern string theorists. Mass is not a fundamental property of matter. Mass is simply momentum hidden in a dimension we cannot perceive.
The winding number n dictates how many times the quantum field wraps around that tiny circular fifth dimension. If the field wraps around twice instead of once, the effective mass doubles.
Right.
Furthermore, it is inversely proportional to the radius r. If the hidden dimension is incredibly tightly curled, a very small r, the energy required to resonate within it is immense, manifesting as a higher mass in our observable four dimensions.
It is a purely topological origin for mass. But notice the time dependence built into that parameter. The mass is proportional to the square of v.
So in the deep past, when v was small and rapidly growing, the masses of fundamental particles wouldn't have been constant. They would have been dynamically shifting, growing heavier as the universe expanded.
Exactly. But in the current epoch of our universe, billions of years after the origin, the parameter v has asymptotically flattened out. It is virtually equal to 1.
So v squared is just 1. Which means the effective mass, as time approaches infinity, asymptotes to perfectly stable value, simply n over r.
Exactly.
In our current late-stage universe, the masses of particles appear totally constant to our instruments. We measure an electron's mass and assume it has been that exact value since the dawn of time. But this model suggests we are just measuring it during a very flat, stable part of its geometric evolution.
And the final piece of the Schrödinger equation is the potential energy term. The derivation yields a constant potential V of Ci equal to n over 2r. This effectively acts as a built-in zero-point energy, a vacuum energy dictated entirely by the topology of the extra dimension.
When you step back and look at the entire mathematical architecture the author has built here, it is a masterclass in theoretical economy. You don't need to invent a sprawling, discrete quantum framework from scratch to explain probability.
No, you don't.
You don't need to invent a Higgs field to explain mass.
If you simply postulate a scalar flat five-dimensional spacetime that is naturally expanding, and you constrain that fifth dimension into a tiny compact circle, quantum mechanics unavoidably falls out of the classical math.
It's incredible.
It is the geometric shadow cast onto our four dimensions by the structural twisting of the fifth.
I think we need to take a breath and recap the sheer amount of ground we have covered today because the logical chain of this paper is incredibly tight.
Let's do it.
We started by taking the standard four-dimensional grid. We added a dimension with a frame-dragging term that intrinsically coupled time to that new spatial axis to flatten the scalar metric.
That coupling was the theoretical heavy lifting. It provided a mathematically safe, singularity-free model to the origin of the universe.
Right. We then defined a toy universe that expands continuously, finding a shrinking pocket of time-like symmetry.
The collapsing thermodynamic umbrella.
Yes. And finally, mathematically manifesting a Schrödinger equation just by compactifying that fifth dimension. Planck's constant was revealed to be a fading function of cosmic expansion, and fundamental mass was exposed as discrete geometric momentum.
It is entirely fair to ask why a theoretical draft like this matters to our overall understanding of physics. After all, it operates on a highly specific, idealized metric.
It's true.
But it matters because it demonstrates a deeply profound philosophical point about a search for unification. We have spent decades trying to brute force quantum mechanics and general relativity together, assuming we're missing some entirely new physics.
Right, like looking for a missing puzzle piece.
Yep. But this paper challenges that assumption. It suggests that perhaps we aren't missing new physics. Perhaps we're just suffering from dimensional myopia. It perfectly illustrates the modern pursuit of quantum gravity, the attempt to show that quantum mechanics isn't a separate rulebook, but perhaps a geometric consequence of a higher dimensional general relativity.
It encourages us to severely question our deepest assumptions, like the idea that fundamental constants are actually constant rather than transient functions of an aging cosmos.
Exactly.
And that leads me to a final, slightly haunting, unaddressed thread to ponder that I want to leave you with today.
Oh, I'm ready.
The culmination of the paper establishes that the effective mass in our quantum world asymptotes to a stable value, the winding number n, divided by the compactified radius r. In deriving this, we and the author make an implicit assumption. We assume that the microscopic radius r of that fifth dimension is perfectly rigid, that it never changes. But what happens to our understanding of elementary particles if that cosmological radius r isn't actually constant, but shifts imperceptibly alongside the expansion of our universe?
Oh, wow. If the overarching architecture of space-time is dynamic and evolving, it stands to reason that the compactified dimensions might also be subject to subtle structural shifts.
Right. Could what we measure as fundamental particle masses simply be geometric shadows of an evolving higher dimension? If R is slowly breathing, then the very foundations of the standard model are quietly in motion.
That is a phenomenal point to end on.
It is something to seriously ponder the next time you look up at the night sky. Thank you for joining us on this deep dive into the source material.
Until next time, keep questioning the geometry of your reality.